Okay, so let's prove it. Okay, so what we're trying to do is we're trying to differentiate this function here. 1 on n plus 1 times x to the power of n plus 1, right? We're trying to differentiate it to prove that rule of integration. So this here is a number, 1 on n plus 1. So that means we completely disregard that, okay? I'm just going to leave it hanging out here. Got 1 on n plus 1. And so then this is what I'm differentiating, x to the power of n plus 1. Well, we just apply the power rule, okay? What it's going to be, n plus 1. So remember that number comes out the front, n plus 1, x to the power of, that number stays the same, take 1. Alright, remember if you have x to the power of 5 and you differentiate it, n, f of x, n take 1. Alright, here we move the power down, there's the power, x, f of n take 1. Okay, the power take by 1. Now let's process this. Okay, n plus 1 multiplied by 1 on n plus 1 cancels. X to the power of n plus 1 take 1. X to the power of n. We've proved it, okay? The integral of x to the n is x to the n plus 1 on top of n plus 1. Now, we're going to use that now. So what we're doing, we're moving from using differentiation to just looking at some rules. Here's a list of rules, and now we're just going to apply them. Just like we did with calculus, right? Although there's a lot fewer rules for us to know. All right, so let's get straight into it. Here we have our first question, the integral of this whole thing. Now, we've said one of the properties of integrals, all right, I'm going to do this in a really elongated manner, but just like calculus, this is sort of a 1-mark question. I'm just going to really draw it out to make quite a few connections. So just like calculus, we can integrate term by term, right? So we could write it like this, plus the integral of this part, take the integral of this part, okay? And the integral of 4x, like we can pull that number 4 out the front, right? We could express that as x to the 3 plus 4 times the integral of x. Take the integral of 2. All right, and even there, I've pulled the negative out the front. I've already preempted it, but I've pulled the negative out the front of the integral statement. Okay, so let's go through and apply that power rule, right? The integral of x to the power of 3 is x to the 4 on top of 4. So that one goes to here. Okay, that's what that term becomes. And then we have plus 4 times the integral of x. All right, well, x by itself is x to the power of 1, isn't it? So the integral of x to the 1 is going to be x to the power of 2 on 2. All right, x to the power of 1 plus 1 divided by 1 plus 1. All right, so that component integrates to that component integrates to that. And lastly, whenever you have a constant and you integrate a constant, it stays the same, but you whack an x on it. And then plus c. All right, so what we've done there is we've integrated without simplifying, okay? Same with calculus. If it wants you to simplify, it's going to be very specific. This here, this can simplify, can't it, right? There's lots of ways we could express it. We could express it like this. Here we have 4 times a half. That's going to be 2 lots of x squared. Take 2x and plus c. That's what it would simplify to, right? Okay, so that's just applying the power rule for integration. Move on to the next one. All right. First, we need to express everything as a power of n. So the cubed root of x means x to the power of a third. And then we've got to take 4e to the power of x with regards to x. All right, we've expressed everything as x to the power of n. Now, we just integrate. All right, so this is going to become x to the power of a third plus 1 on top of a third plus 1. All right, that's what that first term goes to. And then we've got to take away 4, and the integral of e to the x. Now remember, the derivative of e to the x is e to the x. Therefore, the integral of e to the x is e to the x, and that's in our list of rules up here as well. 4e to the x, and then plus c. Okay, so that's integrated without simplifying, but we are going to simplify this one as well because we've got a few tricky fraction operations going on here. All right, a third plus 1. Let's really draw it out, okay? So we've got a third plus, I'm going to need to make them have the same denominator, so 3 on 3, and then divided by the same, a third plus 3 on 3. All right, that's going to be x to the power of 4 on 3 on top of 4 on 3. All right, so we have this whole thing at the top divided by the fraction at the bottom. Remember, it's important to keep track of, it's not x to the power of 4 on 3 on 4 divided by 3, rather it's x to the power of 4 on 3 divided by 4 on 3. Keep in mind, where's the big divider, right? We've got a fraction as the denominator. And so what that means, this is how I think about this when I'm processing this manually, is it's x to the power of 4 on 3 on top of 1. That's what we've got at the top of the fraction. What do we have at the bottom of the fraction? 4 on 3. And then we have our a on b on c on d. I'll write that out again. We lost that one. A, b on b, c. All right, so a times d on b times c. What's it become? 3x to the power of 4 on 3 at the top, on top of 4 times 1 at the bottom, 4. All right, so you can go from there to there, really. All right, what you're recognising, the power is 4 on 3, you're dividing it by 4 on 3, which means the 4 stays at the bottom and the 3 goes to the top. Anything else to say about, we need to take 4 e to the x and then plus c, that's part of the question. Anything else to say about that one? No. I don't want to overcomplicate it. And look, these kinds of fractions operations, you'll have your calculator from now on, right? So if you're not sure, you can do them in your calculator. Yeah, we'll make it easy with the next one. All right, let's move on to C. All right, with C, we have the integral of 3 on x plus 2 times 1 on x squared plus sine x. All right, so here we will integrate term by term. What I'm going to do first is express everything that we can with a negative power, except this one, all right? So let's first just write it like this.
Wasn't it 3 on x?
Okay. Now, like the reason we do this, okay, maybe I'll explain myself, is if we try and integrate x to the minus 1, we're going to have x to the minus 1 plus 1 on top of minus 1 plus. Firstly, we're dividing by 0, and then we have x to the power of 0. So this doesn't exist, right? And if we look at the rule, the integral of 1 on x is ln of x. Okay, so this component here, the reason why, when it's just a power of 1 in the denominator, we don't use the power rule is because it goes to ln of x. So that's 3 ln of x, that's what that part goes to. Here we're going to apply the power rule though. We're going to have x to the minus 2 plus 1 on top of minus 2 plus 1. And the integral of sine of x is negative cos x. Plus c, simplify. Now, I'll write it out like this, 2x to the minus 1 on top of minus 1. Last step. So you can write it like this. Alright, so if you integrate this is what we obtain. Therefore, if you were to differentiate this, you'd get what we started with. Alright, so that's question 1. Let's move on to question 2. 4 cos x, take 3. Alright, so it's written differently, right? It says find the antiderivative with respect to x. what that means is tack on and your elongated integral symbol. What a name for a symbol, right? Integral symbol. Tack it on and you're integrating that with regards to x. You're finding the antiderivative of it, right? So the integral of cos x is sine x, and the integral of 3 is 3x, and then plus c. All right. If you integrate this, this is what you would obtain. So that's 2a. In 2b, in 2b, you'd look at this and you go, we need to express everything as x to the power of n, right? So that means we need to process this using index laws first, all right? And then we can integrate it. So if we're using our index laws, we've got x to the 3 on 2 at the top, and we'll split the denominator as well. All right, one more step for processing. The top power take the bottom power. All right, so all of these are equal, right? They're different ways of expressing the same thing. All right, so we're just using index laws to simplify it, and now we've got it in a form ready for us to integrate because everything is expressed as x to the power of n. So we'll integrate. Here, minus half plus 1 plus c. We'll process that quickly. So we have x to the half on half. Take 3x to the minus 1 on minus 1. Alright, so getting a bit quicker with my simplifications there. 2x to the half we can express as 2 times square root of x, or you can leave it as 2x to the half, either's fine. Um, 3x to the minus 1, I've put the x at the bottom. Alright, any questions about it? So just applying the rules, right? Okay, on to c. 2c. Now here we have x take 2 squared. Right, they want us to integrate that with regards to x. Now, this one, before we can integrate it, we need to completely expand it. Okay, we need to make sure we apply the perfect square rule, and so it's fully expanded, ready for us to apply the power. So, applying the perfect square rule, that's what it expands to, and then we'll integrate. Alright, so I think it might be best, I don't think I can do 3 now if people want, or I can do it tomorrow. 3 is a little bit, it doesn't really follow on directly from the rules. What do people reckon? Should we leave it or should we do it? May as well do it. Hayden's called it, let's do it. So, clear a bit of spacing. So we've got find d on dx of x sine x. Okay, x sine x. If we're going to differentiate that, we need to use product rule. Alright, if we're going to differentiate this, we need to use the product rule. So we've got u corresponds with x, u dash will be 1. V is sine of x, and so v dash is going to be cos of x. Alright, so the derivative of x sine x then is, we'll call it dy dx, u dash v plus uv dash. Oops, don't need that. Okay, so that's the first part. Differentiate it. Hence, find the integral of x cos x. Well, we don't have the integral of x cos x, but let's make the integral statement, and then we'll manipulate it until we can isolate the x cos x component. So, if we differentiate this, this is what we obtain. Therefore, if we integrate this, then this is what we will obtain. Okay, now we're asked to isolate the x cos x component. Now just like differentiation with integration, we can integrate term by term. So let's split that integral up. Alright, so all I've done there is split the integral. Now this is the component that we're after. We want that part by itself. The question says, find the integral of x cos x. And so this is an equation, right? It's a linear equation. We want this part by itself, so we're going to take away, we can subtract, this is some function, some operation, we can subtract it from both sides. We're going to shove that over here. So we're left with the integral of x cos x, with regards to x, is equal to x sine x. Take away, that's what I'm moving over, right? The integral of sine x. Okay, almost done. X sine x, take away. Now the integral of sine x is negative cos x. So it's going to become negative cos x plus c. And so negative is positive, right? That's our answer. We've isolated the integral of x cos x. Alright, so that's a pretty common sort of test question, exam question that pops up. Gets you to perform the differentiation. Alright, make an integral statement. Isolate one component of the integral statement just by performing some linear algebra and processing to get it all by itself. So you'll see this question pop up around question 8 or 9 in the exercise. Alright, any questions? Cool, so I'd like you to do a few of them before the end of the lesson today. So practice the rules, right? Just practice those rules.